Hello everybody, I am the author of Hyperlib, the LEGO Spike Prime Motion Control Library, and in this video I will show you guys how to use Hyperlib and I will go over the public resource and how to study to understand Hyperlib. Alright, so there are two sources. The first one is the reader docs and the second one is the GitHub repository. Now, to access the readerdocs.io page, the documentation, you can visit the link down the description below. Alright, the same goes for the GitHub repository. Let's go to the documentation first. In the home page, you will see the overall idea. So the overall idea of the implementation of odometry into tracking, it is not magic, it is not perfect, it can never be perfect. Doesn't matter how much you tune, doesn't matter how much you change the wheels, doesn't matter the material of the wheel, it will never be perfect because it is an estimation. Alright, and these estimations accuracy relies on the wheel slip. Alright, so I'll just make that clear first so you guys can understand the thing that is going on in here. Alright, and we strongly encourage you guys to build your own function. After you go through Hyperlib, I think you guys can thoroughly understand the basic concepts of coding in Pybricks, and you might get familiar with the mathematical theory of odometry, pre-pursuit, and some other estimation and correction methods. I think that's it. Then let's go to the quick start tab. Alright, in this you can find the repository structure, and when you want to download a code, you wanna go, either you can go like directly from here to the code directly, alright, or you can visit the GitHub repository by clicking on this, Ctrl click to open it in a new tab, go to versions, and you can see all the versions right here. Want to go to latest one and download these two. Alright, I already have two of those down, and these are the setup, which is in the first one in the main program.py. We will be running from main program.py. Alright, and now let's go to the next part, which is the concepts. So there are two types of odometry that we'll be using. The first one is linear, the second one is arc odometry. Well, the linear odometry is when we assume that our robots move in straight line. This does happen sometimes, but most of the time our robots actually move in curves. Really, even though the deviation is really small, it is still a curve. Alright, and we estimate that curve using arc odometry, and most of the time it is more accurate to use arc odometry, but sometimes if the robot just happens to go like super straight, linear odometry will be more accurate. So that's why I include both and alternate between these two based on the condition of the robot. And down here we have geometrical explanation for both. I use Desmos and Paint to explain to you guys what are the variables and mathematical concepts. Overall, these are all secondary math knowledge, so it's not that hard to comprehend. Also, it's only trigonometry. Alright, there's nothing fancy to it, only trigonometry. It looks fancy, sine and radius and stuff. There's nothing really fancy about it. If you go over it, it will be easy, very easy to understand. Let's move on to pre-pursuit. It is a very sophisticated movement function. I could say that. For example, you want to go from point A to point B, but there's an object in the middle and you want a curved path to avoid that object, then you could use pre-pursuit. Most of the time the robots moving using pre-pursuit will be in curved movement, so it will be actually less accurate if you use pre-pursuit, but in some cases you would want to use it to maybe go faster, or maybe if you have waypoints close to the end of the movement that you can use to tell the robot where it is, besides from the encoder readings, of course. Here in the mathematical proof of pure pursuit, you will see these highlighted lines. These are lines that actually exist in the code, all right, in the library, in the functions. A good exercise is that you want to try and pair these equations to those in the functions. Then you will be better at understanding the function overall. Now let's go to API reference. This is a part where it explains all the functions and the variables of the function, the inputs and the outputs, explains what it does. Yeah, all right, and you can go to version history to understand like what have changes between, you know, for example, the latest release is 1.6, right, and it describes what have changed between 1.5 and 1.6. 1.7 will be out really soon. You might want to check that out. All right, let's go to the Hyperlib software. Actually, let me delete all of this to show you guys how the first time setup goes. So just forget about all these. You would wanna load these two. These are the two main programs that you can download from the repository or the documentation, right? Download it to your laptop or your computer, then import it into Hyperlib. All right, now we have these two programs. These two are the two main programs that we are going to use the most. This is where all the functions go and the calculations goes. All right, let me walk you through it really fast. Since I put like a lot of comments here already, you guys can read it to understand. All right, I'll just make a really quick walkthrough here so we don't waste each other's time. So first, this is our the import parts. We import all of the essential functions, essential default functions that Hyperlib give us, and we initialize the hop, and we create our array, our switch, which is just a boolean variable, and our other variables. Here's our kpkd variables, but for our line sensors, our calibrated raw values for our line sensors, as you can see here. And then this will be I think this is the most important lines. You would wanna know which directions is the forward direction of your motor. So when you type your motor, for example, quick check, you type, you make a new program. You make a new program. Let's call it test2, and you import everything from Hyperlib. Import Hyperlib. If the motor is going reverse instead of forward in the direction of the robot, you want to put a direction counterclockwise over here. All right. So if my right motor was reverse, I would put it here also. All right. You want to test that for both motors. Now we have the wheel diameters. Please make sure the wheel diameter is correct, otherwise your odometry estimations won't be as accurate. And make sure that all the ports are correct. These are the motor controls variables. Loop time, which is like the period between the calculations, like how fast we are pulling data from the sensors. I recommend putting it at 10 milliseconds because like I have experimented with different values and I find this are optimal values. It's not so fast that the hub cannot keep up, but it is not so slow that it makes our calculations inaccurate. And we have the max acceleration, like if 30,000 is making your robot tips over when it is accelerating or stopping, then you should lower that value. All right, you should lower this value. And you have minimum speed and maximum speed over here. You would not want to put your minimum speed too slow because like if your robot was on low battery, too low of a minimum speed would stop it from moving entirely. All right, and these are autometry variables. We need to initialize it, so this is where we initialize them. And these are helper functions. These are helper functions that helps with calculation, to shorten our code by a lot. You can read this to understand the logic behind the math very easily. And down here we have the movement functions. All right, these are all movement functions. Quite boring. Actually, I need to focus more on this value. So why do we have to calibrate? All right, why do we have to calibrate the sensor? Well, between the field at your home and the field you have on the competition day, the black and white values can never be the same, and it will never be 0 and 1024 like how you think, right? Because like 0 is minimum and 1024 is maximum. It must go like that, right? The black and white values. But in reality, your value will differ, so you would need to calibrate your line sensor. How? So actually, let me create a new program for you guys. Line calibration. I'll include this in the repository in the next upload, actually. All right, so you want to import and if you want to calibrate and find other values, RGB, and you could find 0 for R, 1 for G, and 2 for B, 3 for W. All right, remember that. All right, and the last one is line mid value. This is where we do single line following, right? So this is the set point between the black and white edge that you want to use. All right, and please drop a star on GitHub repository. Please drop a star right here. It will help me out a lot. Hope you guys have enjoyed this.